Okay, hi everyone. Thanks for coming. So this is a pre-recorded talk for Lean Together 2021. Uh, on the 7th of January, I'll be doing a Q&A session, which will be at 1 p.m. Eastern Time, 7 p.m. Central European Time, as part of one of the social breaks of the conference. So feel free to come along then and ask questions about this talk, or just contact me via Zulip or email or whatever anytime. I'm more than happy to answer questions, despite the fact that you can't interact with me in real time. So these slides that I'm using are online at that web address. So feel free to follow along on those. And yeah, without further ado, let's begin. So what I want to talk about is automatically generalizing theorems using type classes. So what do I mean by that? So I'm interested in two things, really. I'm interested both in making life easier for maintainers of formal libraries like Mathlib, so reducing the human cost to maintaining these libraries and to building them in the first place. As currently it's a bit, it's a bit annoying, a bit slow at times to build such libraries, slower than it should be sometimes. But the other thing I'm maybe even more interested in is kind of prototyping sort of tools that, maybe at some point in the future, research mathematicians might use as part of their day-to-day life. So the computer is an incredible tool that can do things that we can only dream of. They can search far beyond the realm where we would get bored and give up, and they can process certain things far faster than we can. So I want to develop some tools that we can kind of leverage that computational ability to do useful things for a research mathematician, right? So this is sort of my attempt at kind of an early version of something that might one day, I hope, actually maybe provide some interesting insights to people. So what is the problem I've been approaching recently? So it's quite a simple one. So in a library like Mathlib and Lean, a whole lot of different results, and often people write those results with an application in mind, right? So they're trying to prove some big important theorem, and they realize they need a bunch of lemmas along the way. And so they write the lemmas, and if they're a good person, they fill out the whole API for all the definitions they've introduced. And what sometimes happens is that, they make a blanket assumption at the top of a file, let R be a commutative ring. And this is something that we do, obviously, in mathematics as mathematicians. You start a talk with, let R be a ring with a unit, and you leave it there, and you never mention it again. And you don't think, both in pen and paper math and in formalized math, which theorems necessarily use which assumptions. And so that's the problem that I've been approaching. Is quite often in a mathematical library like Mathlib, you have a lot of theorems, and the assumptions are some type classes, some algebraic things about, is it a ring, is it a group, or is it a topological space or a topological group? And it's hard or time consuming to go back and check everything you wrote and check sort of what the generality or the lemmas you've proved holds in. And so what I'd like to do is detect automatically how generally lemmas hold in a mathematical library. So that's the problem. So let's give an example quickly. So this is a lemma in Mathlib. So all my examples will be legitimate examples, as in things which are actually in Mathlib today. And it's not to shame anyone. I mean, there's no shame in writing a lemma like this. But it's just because I want to, give some realistic examples. So this lemma, it's about fin sets, and you've got a linear ordered field, and you're summing the absolute values of some elements of some fin set along some map, and you're actually bounding the sum of the absolute values below by the absolute value of the sum, or whichever around you want to state it. And this assumes a linearly ordered field. Right, that's the standing assumption, alpha. And it makes no mention of inverses, though, in the statement, right? It assumes a field, but there's no mention of inverse in the statement. And it doesn't even mention multiplication in the statement, right? This absolute value thing is something about if it's less than 0, you make it positive, you take the negative, and if it's positive, you leave it as it is. So that's not involving multiplication. But maybe the proof uses it, right? There are many examples in mathematics where the statement, Fermat's last theorem, the statement only involves natural numbers, but the proof involves more complicated objects. Well, this is not one of those examples. The proof does not use anything more complicated than a linear ordered additive commutative group, in fact. Right? So that's the correct type class assumption. Right? And the person who originally wrote this lemma, I assume, needed it for a linear ordered field, and they wrote the lemma for a linear ordered field, and they put it in the file, and that was fine. The problem is, it's not a big problem, but it's an annoyance, perhaps. At some point in the future, someone might want to apply a lemma like this to the integers, right? The integers are a linear ordered additive commutative group, and they might find this lemma and they might try and say exact fin set abs sum less than sum abs and get some weird error message, or they might reprove it and you end up with duplicated lemmas. And so it would be nice if there was some automatic thing that automatically, a linter that took lemmas like this and told us that we were being overly specific in our assumptions. So that's the example. We already have some linters that do maybe sort of similar in spirit things. So the closest one we have is maybe the unused arguments linter. So this is in Lean's MATLib. And this is a linter which automatically tells you, right, it's a meta program that runs maybe once you finish writing your lemmas in your file, you write lint at the bottom, or whenever you push to MATLib, it gets linted. And so this is a meta program which looks at the things you've proved and tells you maybe some problems with them. So it might be that it doesn't have documentation, but in this case, it tells us, this is quite a common one. We, as humans, don't like to divide by 0, so we might try and prove this lemma about groups with 0 by assuming that the thing we're dividing by is non-zero. And in fact, that's not necessary because in Lean, 0 divided by 0 is 0. And so this is an unused argument, and there is a linter which will automatically flag it as such. Right? It will tell you unused arguments, argument 4, a is non-zero. So in this example, we have a meta program that's doing a useful job to us and might occasionally provide us with mathematical insight. Right? It might occasionally be the case that you prove something, maybe assuming that a natural number is prime, and it tells you actually you never really used that fact. So that there are definitely been examples in my experience where a linter has told me something that I've thought, oh, cool. It's been a nice surprise. And that's the sort of feeling I want to evoke. So in the previous example, the argument, though, it is used, this linear ordered field argument. It's not that it's an unused argument, it's just the only times it's used is in the type class mechanism to construct sort of simpler, right, less specific algebraic objects. So in this case, it's used via linear ordered field to linear ordered commutative ring, right? And so the linter that I'm talking about, or that I want to or have made, will not, have to search for unused arguments, but we'll have to search for, somehow within the proof, not just things not being in the proof, but things appearing in the proof only in certain specific ways. The way they appear should be the way that the type class mechanism puts them in there. And so that's what you're detecting automatically. And so the unused argument linter also notices duplicate arguments when one of them is unused, which is also kind of helpful. So how do type classes work, right? That's what this is all about. So when you write a lemma, and maybe you write it in tactic mode or time mode, doesn't make too much difference, and you assume some class as one of your arguments, and then you apply another lemma which assumes some other classes as some of its arguments, the type class mechanism will try and automatically get from what you've assumed to what you're using via kind of chains of these other lemmas or instances that kind of take in maybe a linear ordered field and spit out a linear ordered commutative ring. And this mechanism is very general, and it's used or abused within Lean's MATLib to a huge extent for many different things. In fact, we use it for certain natural numbers being prime and stuff like that, and other kind of small assumptions that we don't want to deal with by hand. And this type class mechanism is what lets us write mathematics in Lean that looks vaguely like mathematics you would on paper, in that you're not stating every explicit invocation of a ring is an abelian group, right? You just sort of stuff is happening under the hood, and it's sort of what makes the verbosity of Lean less than maybe some other provers. And type classes are not unique to Lean. We'll talk more about that later, but they're used heavily in Mathlib, and they're very useful. Right? We don't want to get rid of them. We just want to understand when they've maybe taken too many steps for us, right? That we could have saved it some work. And so it does make it easy to figure out exactly what you're assuming, right? Because this automatic system is happening under the hood. Let's move on. So why is a linter for this sort of thing reasonable, right? So the linter is reasonable. And by reasonable, I mean, why do I think this can actually work? It's because the aim is only to change type class assumptions to match the things which are used in the proof. So ideally, the proof will not need changing, right? Okay, it's possible that if you write a proof script which looks like it was generated by the type class system, then the linter will flag it, and you might actually have to change something by hand, but 99% of cases, the proof will not need changing, because all you're doing is readjusting the assumptions to match what's being used. And so the linter won't really need to do any non-trivial proving, right? It won't need to do any real proof search or any deduction or even any checking of definition of equality or anything like that. And so it should be comparatively fast, right? It's just sort of inspecting the expression that you've provided to it and kind of checking the expression you provided being the proof, and it's checking that that expression doesn't have any sort of chains of type class instances which are kind of too long or something like that, right? Or anything which is not really used in an effective way. And so I'll say more about how it works later. And so, yeah, a meta program which attempted something more general, not involving type classes, just generalizing arbitrary assumptions, would be far more involved and far closer to, genuine automated theorem proving, which is not what this is. This is just sort of a graph theoretic analysis of proofs. So is it worth doing this? I mean, is it just, I'm not all, maybe I'm going to do this and all that's going to happen is I'm going to find 3 lemmas that assumed commutative ring and actually only needed ring. And one reason I think this is worth the effort is because while working on this project, several commits to Mathlib have been made that have fixed several of the things that my prototype linter has noticed. And so I could have saved those people some effort, right? I've seen, between 5 and 10 different PRs, all doing things that the linter in its nascent stage flagged. And so, sort of anecdotally speaking, at least, this isn't only flagging things that no one really cares about. This is flagging genuinely useful improvements to the library, possible improvements to the library. So some caveats before we get into the meat of the talk. It's, of course, possible to write a proof which is inefficient and sort of fools the linter. So in this case, once again, a real example, not to shame anyone, but just because it's good to keep our eye on the genuine real-world examples and not to come up with fake ones. So this thing, we can see the statement here. It's kind of clear that all we're doing in this statement, okay, it's complicated setup, but we're just kind of moving something from the right-hand side to the left-hand side, right? But it's staying on the multiplication sign, the f of y is on the right. And so in this case, we're assuming that we're working in commutative monoids n, but actually that's not necessary. But the proof actually uses commutativity, because when this proof was written, when this app was added to the library, the mol in the left version, which is the one with the commutativity, was proved first by the author. And then they proved this one using the one they already proved and added the commutativity, right? So this isn't, Fields Medal winning lemma, but, it's something that maybe at some point in the future someone might want to apply. and they might get annoyed when they realize that this lemma assumes more than it needs to. So this would fool the linter, because the linter wouldn't realize that this assumption was unnecessary, because the assumption is really used in the proof, even though it shouldn't be. Nevertheless, I think things like this are maybe, it's hard to say how common they are, but certainly there's enough things being shown by the linter that I'm not too worried that we're missing too much. So one other thing is, maybe if we state everything in the most general way possible, maybe the library will become hideously complicated, because we'll be, having to change our assumption. There's something quite appealing about at the top of a file saying, let R be a ring, and R being a ring throughout, and not worrying halfway through about, do you actually want it to be a semi-ring, or now do you want it to be a, something with an add and a distributive law? That might make the library less readable if we're constantly stating everything in more generality. I don't know if that's true or not, but that's a caveat. Okay, so what do I actually mean by the most general type class assumptions? So there's maybe sort of two things I could mean by this. If I've got a type class assumption for my theorem, and I look at all the things it's used, all the things it implies that are actually used in the proof, right? So maybe I've got a ring, and maybe I use the addition, and maybe I use distributivity somewhere, right? Then maybe I could use a semi-ring instead, because I never talked about subtraction, right? This is the sort of game we're playing. So I've got the things that I'm actually using, and I've got the thing which I assumed, and you want to kind of find some intermediate step which still implies all the things you used, but is maybe implied by the original assumption, right? So there's sort of two things you could do, maybe, or at least two ones that I'm thinking about. The first one is to kind of maybe take a meet, right? So you've got some sort of directed graph of different structures, algebraic structures, topological structures, and you sort of take the minimal thing, or a minimal thing, that implies all the things you're actually using. The advantage of this would be that you're doing something unique, right? I'm not going to replace an assumption of a ring with sort of 3 different assumptions. There's no proliferation of additional assumptions, just weaker ones. And it maybe is slightly easier to avoid some of the problems I've been having with sort of multiple inheritance, when you're only taking one assumption to one assumption, and not kind of ever considering the possibility of maybe assuming 2 weaker things instead of 1 stronger one. The second approach is to take all the things you actually use in the proof and sort of find the induced, all the things which are reachable, and finding the minimal elements of that induced graph. So this is what I've been doing. I've been taking this directed acyclic graph of kind of type class assumptions and finding the reachable set from all the things which are used in the proof, and finding the elements with no incoming errors, incoming implications within that reachable subset. So I'll maybe give some examples later, but it's an approach where you no longer have a unique, as one assumption gives you one assumption. The linter might say, actually, you could replace this with 3 different assumptions, and we'll see maybe some examples. But in many cases, these 2 things will be the same. There'll be sort of a right answer here. But it's just a question of, do you want uniqueness of answers, and do you want to consider the possibility of maybe replacing one assumption by 3 assumptions, which are weaker? Okay. What does the lean type class graph look like? Or should I say the mathlib type class graph? Well, it doesn't look like this. This is a small subset. So I made an observable notebook, which I don't really know how to do, but you hack around enough and you can kind of hack something together. So let's just look at this a bit, because it's fun. So this is sort of some algebraic and order structures which are implied by linear ordered field. So just if I've got a linear ordered field, it's in particular a field, which is in particular a Euclidean domain, which is an integral domain, which is a domain. And then where does this one go? Domain, this one all the way up to non-trivial, okay? And then non-trivial is, well, who knows what all these weird things at the bottom are. Maybe these are a bit spurious, but that's the sort of thing that we're doing. And this is the sort of thing you might read on Wikipedia if you read about fields and integral domains and Euclidean domains on Wikipedia. And so we can see we've got a triangle here. So field has a direct link to integral domain, but it also has one via Euclidean domain. And we have a kind of a big square here. And so this is the sort of thing that will cause you maybe difficulty when analyzing this sort of graph, is that you do have all these diamonds, and you want to make sure you're not just well, you want to take that into account. Okay, so just linear ordered commutative rings. So these are the things which I had in that first example. And linear ordered adcom group was the thing which I actually needed in that first example. So the original assumption in the first example was here, and it went through a 1, 2, 3-step process to get down here. And maybe linear ordered adcom group was needed because maybe com group was, or adcom group was needed, and maybe linear ordered cancel adcom mono. Well, you get the idea at this point. Feel free to take a look at this graph and play around, and feel free to make a better version. I would love to see a version which isn't too hacky and overlapping each other and all the rest of it. But it's quite fun just to look at this graph sometimes, I think. Okay. So I've implemented this in Lean. So this linter, it's a work in progress, as it has been for a few weeks now. And it's getting better all the time. Trust me. I just keep finding, more false positives and more false negatives, and I want to improve it. And there's all sorts of different technical gotchas I'll tell you about in a second. But it's implemented using the linter framework, which is really convenient. Had a little difficulty with caching, but I think I've sorted that now. So it caches this whole graph, not just this graph, but the whole graph, which it then explores when it's doing its work. It uses a native red-black LMAP map of lists to represent directed acyclic graphs, like the previous one, and to find reachable sets and to do topological sorts. As was mentioned in the Lean 4 talk, there is this problem now where as soon as you've used native RBL map, you can't prove anything about it, right? So this is a fast implementation of sort of a dictionary of lists type idea, but you can't prove anything about it because it's native and it's implemented in C++. So that just means, it's okay. It just means you just have to trust that my reachable set algorithm and topological sort algorithm are implemented correctly. Unfortunately, really nice maybe before to try and have this nice dual purpose meta programming tools where they're fast enough that you can write tactics with them, but they're also proven. That's going to be great. I'm looking forward to that. So what are some technical gotchas in case you're interested in implementing something like this, or you just want to know why I'm taking so long? One of them is you should inspect the statement as well as the proof. Maybe that's obvious, but it wasn't obvious to me at the start. Sometimes the proof is just REFL. And okay, the REFL, when you expand it fully, it will have one side of the equality in it. But if the kernel is relying on definitional inequality, that's not written in the proof term. And so you can be fooled into thinking that maybe one of your type classes isn't in the proof term, whereas really it is only up to definitional equality. Sometimes things look like they could be generalizations. The most common one is type synonyms, things like multiplicative and additive and order dual. The way I'm thinking about this is, if you've got an addition structure on order dual, it's the same thing as having an addition structure on the original type. And so these things, maybe they look like generalizations, right? The linter is going to go, oh, you didn't need to assume that X had an addition structure, only the order dual of X had an addition structure. Of course, we know those are equivalent. It's just the linter doesn't. So I'm just keeping a list of synonyms which are not allowed. Sometimes the type class mechanism seems to put non-eta reduced terms in its kind of chains. So you have to watch out for that. And there's many more. If you look at the code, it's full of weird edge cases and little things. And when I say look at the code isn't public yet, but I really hope it will be. So now the fun bit is a demo, of course, just so you can see that I'm not making all this up. So here is VS Code with this generalization linter loaded, imported. And so here's sort of maybe one of the most basic examples you can do. So here's a really silly class, foo, which is just a function from x to x. And here's another class, bar, which extends it, and it extends it by saying that this function should be idempotent. That's the right word. And I shouldn't give away the game. Here's a lemma, which is well, okay, it's a ruffle lemma. It's not even an interesting ruffle lemma. It's it's literally just ruffle. But nevertheless, it's clear that here I've assumed bar, whereas I could have only assumed foo because I don't use the property h at all in the proof. And as you hopefully would expect, the linter tells you generalization linter reports, type class generalizations may be possible. This lemma AA bar instance 1 can become foo. Very good. So that's a minimal example, maybe. Maybe a slightly less minimal example is maybe something mn tours of n tours. You've got a semi-ring, and you've got two natural numbers, sorry, and you've got some x, which is n torsion, and you want to prove that it's mn torsion. So here, do some rewrites, use h, this assumption, and ns mod 0, okay. Simple proof, and semi-ring is too strong here, and the linter will tell us we actually only needed to assume add monoid. So that's good. We could change this here to add monoid, and the linter should stop complaining. Very good. It's still complaining about the first one, but no longer about this. But one thing I want to highlight here is that it is sensitive to the proof term. There are other ways of maybe proving the same thing. So let's see if I can just not take too long. My laptop doesn't like zooming, and I'm proving at the same time. Rewrite model stock, rewrite h, and okay, now we're down to m times 0, 0, so that should simp away. Goal accomplished, and now, it thinks semi-ring is necessary now. And that's because for my new proof, I really am using something about semi-rings, whereas in my original proof I wasn't. So in my new proof I just hit it with simp, and simp rewrote the ns moles as moles of casts. Details aren't important, but just to, the proof matters, right? This linter is not magic. If you give a proof which looks like it's making use of a stronger algebraic structure, then the linter will be fooled. So that was a quick demo. Some highlights. Here's a fun one. This is where I really wish this talk was interactive, because I would ask, what are the correct assumptions for this theorem? Once again, this is a theorem in MATLib. It's not too hard to imagine that maybe both these fields could become division rings, right? The linter flags a lot of things where commutativity isn't necessary. But this one surprised me when I first saw it, and I thought the linter was broken. But in fact, this theorem, right? So this one field is characteristic 0, and only the other field is characteristic 0 in the presence of a ring morphism from one to the other. So I say characteristic 0, I meant characteristic p. The correct assumption is that division ring k and non-trivial L and semi-ring L. So the symmetry is broken, and in fact you can get away with not even having a ring for L, and this if and only if about characteristic P is still true. So this is one thing I kind of thought, I would never have known this lemma was true had I wouldn't have ever read this proof. It's kind of hard to read proof, to be honest. I wouldn't have known what the assumptions of any of these theorems were to know that, in fact, non-trivial L and semi-ring L were all that was used. And so this is the sort of thing that makes me happy. Another fun thing is that maybe the linter can guide us to create some intermediate definitions too. So here's one example of some map mol right. It wants to take semi-ring to this combination of classes, and it kind of can't because these classes, they overlap in their fields. But you can kind of see here, adcom monoid, dist group, mol0 class, that's not quite, adding up to semi-ring, right? Because it's not talking about any multiplicative actual unity or even associativity in this case, I think. But you can see here that this is kind of hinting at, maybe we should have a semi-ring without a one class, right? A semi-ring in order to take the place of these three assumptions, right? So when you start to see, things like this repeated by the linter, I feel like the linter is giving us some hints that there's a lot of lemmas that maybe we should invent some new classes for, right? This is another one that I quite liked when I was just looking through it. I should say I haven't run the linter on the whole of MATLAB yet. It's still a work in progress and it takes time to run. And I'd rather get it to be as good as possible and then run it in anger once. And so, yeah, this is a bit of fun. Topology algebra group.lean assumes topological group in a lot of places for a lot of lemmas where you only need continuous multiplication, so you don't need continuous inverses. So there's quite a few of these, and it's kind of nice just to see, you see a lot with the linter, random lemmas get generalized, but it's kind of fun to see that really there's a whole file here that you can almost, not all of it, but some of it you can generalize. And I should say this is naturally an iterative process. So as soon as you remove two strong type class assumptions in one theorem, well, the theorems that make use of that then might become generalizable. So this is going to be iterative. All the things that I've seen so far, once those are fixed in MATLAB, the linter can be then run again and again and again and again. And who knows? Maybe if we're interested, we can get to a point where the linter stops complaining. So a few last words. I've spoken for maybe longer than I should have, but type classes are also used in a similar way in Coq, Isabelle Hall, and Haskell. And I've never seen this attempted before, but I'm not really a, interactive theorem proving trained person. So if you know of anything like this, please do let me know. Future work would be to finish this and PR it in LintMathLib. I'm interested in maybe in Lean 4 whether this meta program would be run maybe not as a linter, but maybe as part of the type class system, right? Because the type class system, it knows itself. It knows more about what it's doing and what it needed, and it has these things maybe in Lean 4 formalized in a much more solid way. So if the type class system could maybe, as it was running, report on each lemma, and rather than being a separate linter after the fact, that would be very interesting. And yeah, maybe things like bundled structures. I don't know how they play well with this yet. I think they don't play so well, and it would be interesting to do that. And so if you have any suggestions as well of other things, I'd love to hear them. So thank you very much for listening for 40 minutes. And you can see a sort of a sample of some lemmas that I've just run the linter on, and it just kind of spat out some of these random generalizations. This I'm just doing just a sort of regression test myself, just to make sure that I don't forget anything that it generalized. So this is just, I'm not intending to PR this branch, but this is just if you want to go and take a look at the sort of things that the linter is flagging, lots of groups becoming monoids, and yeah, you want to see more. There's a bunch there. And so yes, thank you for listening. Thank you to the organizers, the Lean development team, all the people whose tactic code I've repurposed for this. So, Floris, Patrick, Gabrielle, forgetting more people, I'm sure, who I've stolen their code. And yeah, thank you to the whole community. The Lean community, or the theorem proving community, has been a really great thing to be part of recently. And yeah, thank you for listening.